Welcome to the pre-recording of lecture 31 of MCS 572. So it's already lecture 31. So in this part of the course, we are considering pipelining and synchronized algorithms. In this lecture, the focus is on GPU acceleration. So already 31, but I will try to make the lecture as much as self-contained as I can do. The important notion that will be introduced is thread divergence. Some people have the notion that you cannot do any branching with the GPU. That is wrong. With the important class of reduction algorithms, I will explain two different kernels where we can rewrite the original kernel so that it has less thread divergence and will therefore also perform better. So this lecture is geared towards supercomputing and a high performance, although every computer has a graphics card, and I will end with two very simple kernels defined in the high-level, high-performant programming language Julia. Okay, so what is a GPU acceleration again? Why do we do it? Well, we have teraflop performance. GPUs can achieve 1 trillion floating point operations per second. In order for that to happen, one needs to consider instruction level parallelism, and in particular data parallel algorithms. Many threads execute the same instructions but then on different data. So that's the first constraint. And the second condition is that this is really massively parallel, massive parallelism. So typically GPUs have thousands of cores. We need to schedule 10,000s of threads in order to keep the GPU fully occupied and achieve teraflop performance. It is accelerated computing because the functions that will be executed by the GPU will be launched from the CPU. So we have the relation host and device. In this lecture, we are introducing the notion of thread divergence, and minimizing thread divergence will lead to better reduction algorithms. So I started with teraflop performance, but for the class of algorithms that we consider here, we actually are exploiting the high bandwidth of GPUs. So the performance of the algorithms will actually be measured in terms of how close we are to the peak bandwidth performance. And the peak bandwidth performance on modern high-end GPUs is also expressed in terabytes per second. Also 1 trillion bytes that can be moved around per second. Okay, so this was the GPU acceleration in 2 minutes. Let's now look a little bit into greater detail what makes the programming model scalable. So we launch thousands of threads, but the threads are organized in grids. So the grid can be one-dimensional. In this application, it will be one-dimensional, but it can be two-dimensional, three-dimensional, which is often the two- and three-dimensional organizations are often quite useful when it comes to matrix multiplication. A block is an array of threads. So in a way, when the kernel gets launched, we define the instructions for every thread in a block and a block inside a grid. It's up to the warp schedulers how this gets executed. So what is now a warp? A warp is a unit of 32 threads. So typically we will organize our blocks in multiples of 32. So the warp size has been very consistent among the high-end GPUs. Always has been 32. So the role of a streaming multiprocessor is similar to a core on a CPU, on a multi-core CPU. So threads function very rigidly within a block. Streaming multiprocessors can execute multiple types of blocks and multiple types of kernels. So there you have then again the same flexibility as on multi-core. Here is a picture how the streaming multiprocessor pipeline works. So there are several blocks of threads. The blocks are subdivided into warps, units of 32 threads. Typically, one streaming multiprocessor has slots for 64. So the Kepler architecture had 13 streaming multiprocessors, or 14, of 192 thread slots. Pascal and Volta was reduced to, or at least Volta was reduced to 64. So it was therefore very useful to have at least blocks of 64 threads. So there are the memory hierarchies. So typically one loads the data from the main memory into the shared memory, and then from the shared memory into the registers. So this is also where the pipelining comes in. The warps can be are multiples. The warp is a 32, but you can write a 32 as 8 by 8, for example. Then you have 2 warps. So in the example, if you have the 8 by 8 block, so a 2-dimensional block of 64 threads in total, then the threads are indexed according to the example that is at the last 2 bullet points here. So we have 2 warps, and every thread has a first name and a last name. The first name of the thread is the thread index, the position within a block, and then the last name is the block index. So there is the thread idx.x and the thread idx.y in the CUDA, the Compute Unified Device Architecture model that we use on NVIDIA GPUs. Okay, here is a picture that I stole from the NVIDIA white paper. So there is the out of order, or though in sequence. So you can see that the instructions are in order, in the sense that instruction 42 is not executed before instruction 11. So there is the dual warp scheduler. This would be corresponding to streaming multiprocessors with 64 slots for the cores, and in time all the instructions are executed. Now you may wonder why the instruction is like this, why, for example, one instruction is scheduled way before the other. For example, 33 comes right after 11. This often comes because of the latencies. So sometimes one block of threads has to wait for its data to be available, and in the meantime something else can be done. So here is the reasoning why this is so fine-grained. So there is often a global memory access. So if you are scheduling, say, 256 threads, and even if you have only a dual warp scheduler, then it could be that some of the warps from the first are waiting for the data to be available to be loaded into shared memory. So that's another advantage why you would take advantage of the extra instructions that you need to execute, loading into the data first from global memory into shared memory, and then from shared memory into registers. Looks very cumbersome, but it generates more instructions. More instructions that can be executed. So even if only at the very same time only 64 threads can execute it by one streaming multiprocessor, if you have 256 threads scheduled in a block, then some of the warps can already execute while other warps are waiting for their data to load into either registers or into shared memory. So introducing extra instructions is known as latency hiding. Another type of latency hiding may be that you break up one instruction into multiple stages. Instead of one single instruction, you then have multiple instructions, which is also beneficial for the massive parallelism. Okay, so then we get to branch instructions. So in an earlier lecture, we saw that even at the very highest level, if you have a for loop with if instructions in there, that may prevent an efficient execution. So even if you are not doing parallel computation, the inside the computer, so we have the pipelining of a floating point operation. If you have an if statement in there, so if you have an if, then it's quite difficult to keep the pipelines busy. So there is already branching that can happen at the level of the kernel launches. So if you have an if instruction, then it's actually you can launch from the host in case one of the one kernel or the other kernel. So in a way, GPU acceleration and data parallel algorithms are one of the important classes of synchronized computations. Okay, so this slide indicates the notion of zero overhead thread scheduling. If you have broken up sufficiently fine your instructions, then you can tolerate branching. So why is branching? So here is another example. A little bit out of order now. So we have seen the matrix-matrix multiplication, which is an extremely convenient operation to exploit the teraflop capabilities. If you are going to run, so even if you have already predefined your kernels, you still should try to optimize for the best way of your thread dimensions. So you can schedule your blocks in 8 by 8, 64, and then you have many blocks. If you have a small number of threads per block, then you have to have more blocks. Otherwise, you can deal with fewer blocks. It depends on how many streaming multiprocessors that your GPU has. That is one of the so I was confused earlier between 14 and 13. So the C2050 had 14 streaming multiprocessors, where you had 13 cores per streaming multiprocessor. So that made for 14 times 32 cores. The next level, the Kepler architecture, had 13 streaming multiprocessors, but 192 cores per streaming multiprocessor. So these type of considerations you need to take into account. Now, if you also need to take care of the size of the shared memory. So the shared memory is limited. Also the number of registers. So we will deal with this in a later lecture, that you can get a performance cliff. So you can size up your computations, but at some level threads can no longer be scheduled because of your available register blocks. Okay, so now we get to the central notion of thread divergence. So we have the single instruction multiple data. So data gets ultimately loaded into registers, even if you don't see it explicitly. We have the local variables. So the style of execution makes for a scalable model. So if you have many threads, many cores per streaming multiprocessor, or if you have multiple many streaming multiprocessors and a relatively few number of cores, you can very easily adjust the number of blocks and the dimensions of your grid. So the bottom line again is that you need a large number of threads. So this is the limitation. For massively parallelism, we need to have many high dimensions. So typically we do this with problems that are also sufficiently large. Okay, so now we get to the preparation of the thread divergence. So if you have an if-else construction, then every warp follows actually the same instruction. So if you have an if-else instruction, it works best if all the threads actually have execute either only the then or only the else. So in that sense, you actually don't have an if-else statement. So this seems to be very confusing, but I will give an example with the parallel reduction, where you can set it up that actually all the threads in one warp will actually follow the then part and not do the else. So in that sense, you can have if-else statements without any penalty. Otherwise, you can still have an if-then-else construction, but then the warp needs to be run twice. So once where the part of the threads execute the then, all the thread indices say with the first half, and then the other half will be executed in the else. Again, it seems now that your code is going to take twice as long to execute, but that's not necessarily the case. If you keep in mind the concept of zero overhead latency hiding, when you have sufficiently many instructions, for example, the loading into shared memory, the loading from shared memory into registers. If the if you have sufficiently many parallelism to keep your GPU fully occupied, then if-else statements may not lead to a loss of performance. Okay, so here is one of the central slides in this lecture. So, given the fact that some threads in a warp execute the then part, other threads execute the else part. So in some sense, with the reasoning from sequential code, this is perfectly natural. But in the parallel world, this is a contradiction. This gets resolved, this contradiction, by running the warp twice. So you make two passes in the same code. And that increases the execution time. And that means that the threads diverge in their execution, and we speak of thread divergence. Alright, so there are other examples of thread divergence. If you think about running an iterative algorithm, then on some data elements you have already convergence after 6 iterations, and on other data elements you have already, you need to do 7 iterations. So then every thread actually needs to pass through that 7th iteration. Conditions can be very expressed very naturally by if statements, just like in any language. And again, thread divergence is likely to occur and is unavoidable if we think of the important class of reduction algorithms. And this is the second and actually main part of this lecture. So let's look at reduction algorithms. So again, the algorithms that we are considering now are going to be memory bound, unless you would consider multi-precision multiple double arithmetic, which we will not do here. Okay, here are two examples. So we can make the sum of a vector, or we can take the minimum and the maximum element. When we considered MPI, so MPI actually provides constructions to do these reductions, so the message passing interface with distributed on distributed parallel memory computers. There are also we covered one lecture on the prefix sum on shared memory. So this part here continues this, but then with GPU acceleration. We have covered Brent's law. Brent's law says that if you reduce n elements, you can do this in a logarithmic number of steps. So this is with this model of computation of the parallel random access machine. Typically a reduction algorithm does only one one floating point operation, so they are not compute bound, but memory bound. Now the memory bandwidth is already also expressed in terabytes per second. So also here you don't really speak about teraflop performance, but you speak about terabyte performance, which comes down to the same. So you can process trillions of numbers in a second. Alright, so we are in March. I don't watch sports, but there is March Madness. So a tournament is another application of where you take the best of a group. And here you see that the natural organization to line it up in a tournament is with this tree-like fashion. Alright, so let's then look at our first kernel, which uses these tree-like model. So we have 32 numbers. 32 is 2 to the power 5, And you see that we have 5 layers. In the first layer, half of 16 threads are actually summing two numbers. In the next layer, we have 8 threads that we can occupy. In the middle layer, 4 additions are being done. And in the next to last layer, we have 2 threads that are busy. And in the last layer, we have only 1 sum. So we can see it in this way. So 32 and 5 is not really that big of a reduction, but think about 1024 and then you have 10 steps. So 124 divided by 10 is quite, so this is a 100-fold speed up. Another way to look at this is to look at what we call the stride. In the first level, we sum up adjacent numbers, so the stride is 1. Then the stride doubles to 2. We sum up numbers that are 2 apart. Then in the middle layer, where we have 4 additions, the stride is also 4. And in the next to last layer, the stride is 8, and then it becomes 16 at the very last layer. Okay, so this is our first algorithm. So the numbers are loaded into shared memory. So there is this keyword shared. So I'm using the syntax from CUDA, from the Compute Unified Device Architecture. At the end of this lecture, I will switch to Julia. Here you see the very straightforward C definition, starting with stride equal 1. And this gets executed by all threads in the grid. And we have a one-dimensional thread organization. So every thread in a block has a unique identification error, identification number that will sum up the numbers in its thread. So the stride is limited by the block dimension. The stride doubles in each step, starting at 1. And you see the synchronization that is necessary. So some threads will have to wait for all the other threads. That's because of the in place. So the number gets in the array gets replaced by the sum. And therefore, in order to proceed to the next level, one must have this level of synchronization. You can see the so this is not the prefix sum, but only the threads which thread index are actually a multiple of twice the stride participate. So when the stride is 1, only the even index thread numbers, only the threads with even numbers are doing the sum. So this is not the prefix sum that we considered before. So you have this thread divergence. So when the stride equals 2, then only those threads where their index is a multiple of 4, they participate, they do the sum. Okay, so this is a correct way of summing, but there's a lot of thread divergence. So if you think about 32 numbers, you will actually have 10 passes that you will need to execute all the threads. So it's still logarithmic, so it's still almost constant. If you think about a billion numbers, it will still be a lot faster than if you would do the summation in a linear fashion. Okay, so how now organize it where you have less thread divergence? And in some sense, it's a very straightforward. idea. So instead of starting with stride equal 1, you start with stride equal the dimension divided by 2. So here I'm limited with what I can show on a slide, but imagine now that we would have blocks of thread of size 4. So then only in the last 2 steps you would have thread divergence, because as you split up the summation, so we have 32 numbers, we would have 8 blocks of each of 4 threads. Then all the 4 threads would do the same instruction in the same time. And this is also now a prefix sum. So now you see that 16 threads are busy, and that means the 16 threads in the 4 first blocks are actually all executing the if statement. And the others are actually all doing the else. So this is the case where you kind of have the if-else, which is explicit in the definition of the kernel, but it doesn't lead to thread divergence because of this different reorganization of the strides. So at the first step, the stride is 16, or in general, the number of elements divided by 2. And then in each step, we divide the stride by 2, and in each step fewer and fewer blocks of threads are doing any computation. And at the end then you have again thread divergence. But you can say that the thread divergence only happens if we now think again big, if we now think about summing billions and trillions of numbers, then it will only be in the last warp where you have in the last 5 steps, in the last 32 instructions, where you have the thread divergence. So thinking about 1000 numbers, you have 10 steps. So instead of having 20 steps, you have 15 steps, which is an improvement. If you think about 1,000,000 numbers, where you would have 20 steps instead of 40, you will have 25. 30 with 1,000,000,000 numbers, you will have 35 instead of 60. So you get the picture. So here is the revised kernel. So there's still the synchronization that is happening. Dividing by 2 can be expressed quite efficiently with shifting, so which is indicated by this larger operation in C. You still need the synchronization, but you will have less thread divergence. And the performance of this algorithm will get closer to the memory bandwidth. So there is also this zero latency again. So there is again the loading of the array into shared memory. So that's an extra instruction that is not shown here. Okay, so here you see the reasoning for why we have less thread divergence. Explained in words, what I tried to explain earlier, and I don't think that at this stage I have that much to add. If you have 1024 threads, 1000 is 2 to the power 10, so the 2 logarithm is 10. So instead of having 20 steps with the first algorithm, where every warp needs to go through the if and to the not if statement, so the else is actually explicit. So the else is when the if is not satisfied. I should probably have pointed this out. So you have then no thread divergence here in the first step. So instead of having 20 steps, 20 being 2 times the 2 log of 1024, you will have 15 steps. So not that much of an improvement, but still it is noticeable. And the reorganization is actually quite straightforward. You can still improve on this, avoiding the synchronization. So the synchronization is still needed in the last warp. The last warp uses also a for loop, but instead of doing this with a for loop, you can enroll. So you can actually really have the 5 instructions, one after the other. So that's the idea here, so that's why I repeat this picture again. So now we really have 32 numbers to sum, and we sum them in this pattern. Here you see the code for the loop enrolling. The synchronization of the threads is no longer needed, as every thread now actually executes this, does these 5 instructions. So that means that you can really do this in a logarithmic number of steps. So I copied this from a reference that I'm going to cite in the next slide. This can be programmed up in full generality, where we use C++ templating. In running this and measuring the performance for all the different, so we actually now have 3 different kernels. The first organization, the second one, and then the loop enrolling of the last warp. Here is the bibliography, so there are slides available from Harris, and then there is also the technical report that details the CUDA syntax from the done on the NVIDIA GPUs. So this is a historical paper, more than 15 years old. It's a very good and recommended exercise to do this on modern GPUs, which are actually already approaching or are crossing terabyte performance. Okay, so let's end. So the purpose of this course, and actually the purpose of this whole lecture, is to get you started. So every computer actually does have a GPU, and in the high-level language of Julia, there are several packages available. So I'm using here Metal because I'm running this on an M1 MacBook Air. There is the CUDA, which I will demonstrate as well, but then there are also 2 other. There is the One API, and then there are also for the AMD GPUs. So here you see the kernel to do the enrolling. So every thread will execute the 5 instructions that are defined here. So this kernel is plainly expressed in the Julia syntax, and it is correct. At first I was struggling with the acroll inbounds, which does away with the checking of the indices. So don't expect any performance here. It will be actually quite slow, but it's the principle that matters. So if you are new to GPU acceleration, it's quite an accomplishment to understand why this code is correct. So this is data parallelism. The ith thread will, in a block of 32 threads, will execute the instructions on the ith data element, replacing the ith element each time by the corresponding sum of the ith element with what is at the right hand side, corresponding to the pictures that were shown earlier. So the code itself is extremely short and executes with Julia and then the name of the Julia program. Here are the definitions. So on the M1 MacBook Air, I'm using 32-bit floats and I'm padding with zeros. So actually I'm having an array of 64 bits. So the x underscore h is the concatenated first array of the data elements. So the first 32 elements that I want to sum, padded with 32 zeros. So actually the 32 was actually not strictly necessary. 16 would have sufficed because we have the plus 16. If you do not do this, you may see some very strange numbers at the very end. So we run this with this acrol metal indicating the number of threads. And that will change the device, the data on the device. So we do the memory transfer from the host to the device by the simple creation and declaration of the MTL array. So it's important still in the mindset of accelerated computing. We have all the data on the device, and we also have to duplicate the data on the host. So there are also the memory transfers from the host to the device that are actually taken care of in two ways. So we have the x underscore d, where it first appears. This is where the memory transfer happens from the 64 numbers from the host to the device. And then there is the array that is applied to the x underscore d. So you cannot directly print the x underscore d with the array construction. You create actually another array on the host where you do the data transfer from the device onto the host. And you can see the correctness. So the sum of the first 32 natural numbers is 528. People are working on kernel abstractions, but here I'm just doing it again with now the package CUDA for an NVIDIA GPU. What changes is, of course, the using CUDA and then the thread IDX that needs to change. Also here, the acrol inbounds, so that macro that kind of skips the index checking, did not work here. So everything is still under development. I hope that this will all improve, but for our purposes, this is great for starting to reason on how it works and what actually all happens. So the padding happens also here. The array is the same at the very end. So the transfer from the device to the host is implemented by a constructor. And there is the replacement of the MTL array by the CU array. So that creates the data on the device. When you implement in C or C++ with CUDA, you have to do the explicit allocation and you have to do the explicit memory copy as well. So then, of course, we have the launching of the kernel with 32 threads. We have seen earlier examples where you can specify with CUDA the number of blocks and also the number of threads per block. So on Pascal GPU, it could be very useful to check this for a billion of numbers. And actually to check this, whether you actually would see a difference in the performance if you compare the first type of kernel with the second type of kernel. And that is essentially what is left as the exercises. So we have covered the concepts that were explained in the other textbook that we are following on programming massively parallel programmer. So this is the textbook here that I can flash up. So I'm following this book here, second edition. Also followed the work of Harris. And the purpose of this lecture is to get you started. So especially exercise 2 is actually very much recommended. See if you can. So I started with the summation algorithms. I only did this with block of 1 threads, and actually I did the loop unrolling. So I did the last optimization. So the goal is that we can do this for useful applications. So one application is numerical integration. So if you want to compute the area under a curve, then summation algorithms are always necessary. And here actually the problems may become compute bound, because there every thread has to execute potentially another program to evaluate a function. So and these algorithms are actually very suitable for GPU acceleration. So you can combine then the best of both worlds. So you have the arithmetic capabilities, the teraflop capabilities from the GPU, combined with the fast memory bandwidth, also now expressed in terabytes per second. Okay, I hope this was interesting. So this was in a sequence on pipelining and synchronized computing, although it could also serve as a more or less self-contained introduction to GPU acceleration. So we still have 2 more lectures scheduled, mainly on the avoiding of bank conflicts, and then also on the performance monitoring, keeping in mind the resources, the number of registers that you have available on a particular type of GPU.